Hi, this is a short video describing my paper, Population and Welfare, that's joint with Mohammed Adhami, Mark Bils, and Pete Klenow. So growth economists typically study per capita outcomes, and that's for many good reasons. There are lots of reasons why per capita GDP, per capita consumption is a good measure. On the other hand, from other perspectives, it can seem odd. So for example, imagine two worlds. One has 1,000 people and the other one has 1 billion people. And otherwise, these worlds are identical. They both have the same per capita income, per capita consumption. Well, in some sense, it seems like the world with 1 billion people instead of 1,000 people is better. And from that perspective, per capita consumption, paying attention to per capita outcomes, puts zero weight on having more people, and that can seem extreme. Okay, let me give you another example. Consider two countries that have the same time path of total factor productivity. They have the same resources that are available to spend, and one spends all its resources raising per capita consumption but keeping population constant, and the other does the opposite. The other keeps per capita consumption constant and spends all its resources raising population. Well, we typically look at these and say the first country's the growth miracle and the second country's the growth disaster. But I kind of told you from the beginning they had the same production possibilities, and so maybe it's odd not to think of them as being, much more similar. Okay, well, this example is not entirely hypothetical because, at least qualitatively, something like that's going on in Japan and Mexico. So since 1960, Japan has grown rapidly. It's 6 times richer on a per capita basis. Mexico's had modest growth. It's 3 times richer on a per capita basis. On the other hand, Mexico's population is 3 times larger, while Japan's population is only 30% larger. Okay, so we typically look at these countries and say Japan is the growth miracle and Mexico is below average. But what about the extra people? And so the question we're considering in this paper is how should we value population growth, and can we construct a broader measure that incorporates both the additional people as well as the per capita consumption? Okay, the simplest version that we have to make this point is the setup here. So imagine CT is consumption per person. U of CT is the flow of utility enjoyed by each person with consumption C. And the economy has NT identical people. So there's no inequality, no heterogeneity. We'll relax some of these assumptions later. Summing over the people, if we have n people with flow U of C, the aggregate flow of utility is just n times U of C. And this is the perspective we're going to take in order to value the gains in population, the gains in per capita consumption. In particular, we're going to use this aggregate flow of utility to create a consumption equivalent growth rate. Okay? And so one other thing to say about this, notice that this is not some lifetime perspective. It's not the present discounted value of lifetime utilities. Instead, it's a flow utility measure. It's a flow, how much utility is produced in this year. And in that sense, it's analogous to GDP, which is also a flow concept. Okay. Taking logs and derivatives of this expression, the growth rate of W is just the growth rate of population plus the growth rate of consumption multiplied by an elasticity. It turns out, as we show in the paper, if you want to express welfare growth in consumption equivalent terms, the way to do it is to rearrange this equation so the coefficient on per capita consumption growth equals 1. That's what we've done in the box. And what it says is that consumption equivalent welfare growth is the sum of per capita consumption growth and population growth, where population growth is valued with this coefficient V of C. And if you look at this coefficient, it's actually quite intuitive. The numerator, U of C, is just the utility flow you get from having one more person live one more period. That's the extra utils. We need to convert it to consumption units, so we divide by the marginal utility of consumption to do that. And because we're in growth rate space, we express it as a percentage. We divide by per capita consumption. So what V of C is, it's the value of having one more person live for 1 year measured in years of per capita consumption. This will become clearer in a second. Interestingly, what it says is a percentage point of population growth is worth V of C percentage points of per capita consumption growth. We're valuing people with this V of C. And obviously, the key question then is, how do you determine V of C? What does V of C look like? Well, to get V of C at one point in time in one country, so for the United States in 2006, we're going to use conventional value of life statistics that the Environmental Protection Agency, the Department of Transportation, these are used in lots of other studies. According to the EPA, the typical American had a value of life in 2006 of $7.4 million. The typical American maybe is 40 years old and was expected to live for another 40 years. So to get the value of a year of life, we divide this 7.4 million by 40, and we get a number of $185,000. And this is a very conventional value for a year of life that health economists use all the time. Per capita consumption in the US is a number like 38,000, and 185 divided by 38 is 4.87, almost 5. What this says is each year of life in the United States in 2006 was worth approximately 5 years of per capita consumption. And that's kind of surprising from the perspective of our paper in that it says that each percentage point of population growth is worth 5 percentage points of consumption growth. You might have expected this coefficient on population growth to be some small number like a quarter or a tenth or something, but no, no, no. For the US in 2006, that coefficient is 5. And so it's going to make a big difference that we're adding population growth valued this way. Okay, to get V of C in other years and in other countries, it would be great if we had value of life numbers for all the other years in all the other countries. We don't have those, so we're going to take a shortcut, which is to use a utility function to extrapolate away from the US in 2006. So for our baseline case, we'll assume log utility. With log utility, notice that u prime of c times c is just equal to 1. And so v of c is just u of c. So what are the units of the of u of c when it's log utility? It says it's the value of life units. Notice also that v of c is an increasing function of c. The value of life, even measured relative to per capita consumption, increases with per capita consumption here. Okay, to get the U bar parameter, let me not spend much time on it, but that's where, the V of C in 2006 allows us to calibrate U bar. Okay, so that's where that U bar parameter is doing there. Okay, because consumption grows exponentially over time, typically, the log of consumption grows linearly. And here's what V of C looks like for the US over the last 200 years using some data from Angus Madison's and his co-authors, right? What you could see is V of C in the US today is a number around 5, and 200 years ago, it was a number around 2. So the value of life has grown, but over this 200-year period, it's a number between 2 and 5. When we look across countries of the world in 2019 using the Penn World Tables, we get a similar range, actually. The US and Germany have numbers close to 5. The poorest countries of the world have numbers around 2. And so what's the coefficient that belongs on population growth in these studies? Well, it seems like it's a number between 2 and 5, depending on which country and which time period you're looking at. In particular, it's a bigger number than you might have expected again. So population growth is going to matter here. All right, so just to recap, our consumption equivalent welfare measure is going to be the sum of per capita consumption growth, the usual thing we look at, and population growth, where each unit of population growth is valued with this V of C, which if you think about it, it's exactly the way people themselves value living. That's where these V of C estimates come from, okay? Notice now you can see why V of C equals 0 is such an extreme, corner here. Putting 0 weight on lives seems very extreme, but that's what focusing on per capita outcomes does. If V of C were equal to 1, that would say consumption equivalent welfare growth is just aggregate consumption growth. You might have thought the aggregate consumption is a thing we could look at, but what this calculation that I've done above, where I see that V of C is some number like 2 or 3 or 5, what that says is no, aggregate consumption growth is too conservative. The model wants an even higher weight on population growth than aggregate consumption would imply. Okay, so what we do is we calculate consumption equivalent welfare growth for our more than 100 countries from 1960 to 2019, report the average annual rates. Rather than focus on these summary statistics, let me focus on some examples. So Mexico between 1960 and 2019 had an average annual consumption growth rate, per capita consumption, of just under 2%. So again, slightly below average for the world as a whole. Its population growth, though, was more than 2% per year. And its value of life, Mexico's kind of a middle income country, was a number like 3.4. And so the contribution of population growth to consumption equivalent welfare growth is nearly 7%. And consumption equivalent welfare growth overall is 8.6% per year. Mexico goes from being below average to one of the faster growing countries in the sample that we look at of 100 countries. Okay, let's turn to the United States. 2% per capita consumption growth, 1% population growth, those are kind of familiar numbers. The value of life in the US over this period averages more than 4. And so you're adding more than 4 percentage points of growth from the population term. And so the US looks like 6.5% per year. Consumption equivalent welfare is doubling roughly every 12 years according to the United States with these numbers. So growing very rapidly. 6.5% turns out to be about average for the world as a whole. What about China? On a per capita basis, of course, China is one of the growth stars of this period, 3.8%. Population growth, a little bit, low, 1.3% per year. But importantly, because China is a relatively poor country with GDP per person around a quarter of the US, the V of C is lower in China, 1.8 instead of, say, 4 or 3. And so population growth only adds 2% to China's consumption equivalent welfare growth. China ends up being below average for the world as a whole. A country that's a growth star ends up below average. Ethiopia, 2.5% per capita consumption growth, really rapid population growth. But Ethiopia is so poor that the V of C for Ethiopia is, 1 or a little bit below 1. And so Ethiopia, despite adding all these people, ends up without a particularly high, below average consumption equivalent welfare growth. Finally, Japan and Germany. Again, two other growth stars in terms of per capita consumption growth rates. But look at the population growth rates, 0.5% per year in Japan and only 0.2% per year since 1960 for Germany. So even though these are rich countries, the V of C is high, population growth adds very little in these countries, and they end up being well below average. Germany is one of the slower growing countries in our sample. And so population growth, adding it with the value of life, V of C, gives you a very different perspective on what growth looks like. Another way to make that point is with this chart that shows you where countries are in the growth distribution. What percentile is each country in the growth distribution? In blue, we have the consumption growth, per capita consumption growth. And in brown, we have the consumption equivalent welfare growth. So start on the right with the blue numbers, right? So Germany, Japan, and China are the growth stars on per capita consumption. And so they're in roughly the 80th percentile of the growth rate distribution since 1960. Mexico, South Africa, and Kenya, by contrast, are well below average, say the 30th percentile, picking on South Africa, of the growth rate distribution. These are the slow-growing countries of the world. But if you look at the brown bars instead, it's almost the mirror image. Right? Mexico, South Africa, and Kenya suddenly become some of the rapidly growing countries. Mexico at the 90th percentile, South Africa at the 80th percentile, and Germany, Japan, and China are all well below the median, with Germany coming in at the 10th percentile, Japan coming in at the 30th percentile, and China below the median again. Okay, so how one constructs growth measures, whether you have a per capita perspective or a broader measure that values people, turns out to give you a very different picture. Okay, that's the main finding of the paper. Let me step back a second and say what we're doing and importantly, what we're not doing. So this approach of using the aggregate flow of welfare studies the marginal benefit of people. Okay, we value people according to some marginal benefit calculation, but we say nothing about the marginal cost of producing those people. Answering many interesting questions that you might want us to answer requires specifying the production side of the economy. Maybe the externalities that people create ideas, maybe the production of human capital, maybe pollution and global warming, and the costs of fertility. We're not saying anything about the production side. We're not saying anything about the marginal cost of people. And so in this paper, we can't say anything about optimal population or was the demographic transition good or bad. To be more specific, our paper can't say anything about whether people in Japan should have more kids or fewer kids. We don't have the marginal cost side of the model, so we can't make any statements like that. Those kind of statements are beyond the scope of this current paper. Okay, what we do in the last part of the paper is study robustness. So we made some strong assumptions at the beginning. What if you relax those assumptions? What if we double or cut in half the value of life that we're using in the US in 2006, for example? What if we, instead of using log utility, look at other utility functions, constant relative risk aversion parameterized by risk aversion gamma? What if we incorporate inequality? So you might wonder, well, Mexico's adding people, but maybe it's disproportionately poor people are having kids, so the consumption of the people who are being added are poor, and using the average consumption to value lives might be making a mistake. So we incorporate consumption inequality. It turns out to have a relatively small effect of around 2 percentage points per year out of, say, 6 or 8%. So it's pretty small. We also adjust for migration. And again, in some places, Hong Kong, Ireland, and Mexico, this can matter by 1 or 2 percentage points, but it doesn't change the perspective that I've given you in the baseline calculation. Here's just another way of summarizing some of these robustness checks. The first row shows you per capita consumption, the per capita perspective on economic growth. And the next, 8 rows show you various robustness checks. And you can see, what value of life one uses matters. So is the right number 6% for the world as a whole, or 4.5 or 10? Well, it depends on how you value lives. But all these numbers in this table look very different than the per capita numbers that we usually have. So we can't tell you one number is the right number and all the other numbers are the wrong number, but it does seem that valuing people matters. Finally, this perspective on Ethiopia, where the value of life was very low in Ethiopia, you might wonder, what if we use the same V to value people in all countries? The last 3 rows do that. And again, which V you choose matters, but Ethiopia's rapid population growth could imply, really rapid consumption equivalent welfare growth if you value those people with the V from the United States in 2019, for example. Okay, and then the last thing we do in the paper, which is kind of important and gets a fair amount of attention in the paper itself, is we ask the question, well, what if parents have kids because they love them, and we study endogenous fertility? So that's important. We bring in a quality quantity trade-off. We bring in education. We bring in leisure time. And this requires us to write down a richer framework and use microdata on time use. We can only do that for 6 countries for a relatively recent period. So the last part of the paper is this sort of richer structure with richer data. And to summarize, you could look at the numbers in green here. And the richer structure is interesting. You can see the quality quantity trade-off. You can see that leisure matters for some places. But by and large, we get kind of similar numbers, whether we do it with the simple approach at the start of the paper or this more sophisticated approach that takes into account other effects. Okay, so let me just conclude there. What do we take away from this paper? Well, the usual per capita perspective that is useful for many reasons is not the only perspective one can have. And what our initial exploration in this paper suggests is that if you value people as well, you can get very different answers. And so I don't think this is by any stretch the last word on this question, but we do hope it gets people to think more about this topic and how population growth can influence broader measures of economic growth. Okay, let me stop there. Thanks very much.